Hello and welcome to Electro Nerds Academy. In today's video, we'll learn how to measure temperature and humidity using the DHT11 and DHT22 sensors with an Arduino. The DHT11 and DHT22 both belong to the popular DHT family of digital temperature and humidity sensors. At first glance, they look almost identical, but there are some important differences in their performance and capabilities. Both sensors operate within the same voltage range, that is from 3 volts to 5 volts, and consume a maximum current of about 2.5 milliamps during measurement. The DHT22 is the more advanced and more expensive of the two. It can measure temperatures ranging from minus 40 degrees centigrade to positive 125 degrees centigrade with an accuracy of approximately plus minus 0.5 degrees centigrade. In comparison, the DHT11 operates only between 0 degrees centigrade and 50 degrees centigrade and has a lower accuracy of about plus minus 2 degrees centigrade. When it comes to humidity measurement, the DHT22 once again outperforms the DHT11. The DHT22 can measure 0% to 100% relative humidity with an accuracy of plus minus 2 to 5%. Whereas the DHT11 is limited to a range of 20% to 80% and can be off by as much as plus minus 5%. Despite its limitations, the DHT11 has one notable advantage over the DHT22. It can take measurements more frequently. The DHT11 has a sampling rate of 1 Hz, meaning it provides a new reading every second. The DHT22, on the other hand, updates only once every 2 seconds, or 0.5 Hz. Inside the upper plastic casing, both the DHT11 and DHT22 look more or less like this. Here we'll find 2 main sensing elements, an NTC thermistor for temperature measurement and a capacitive humidity sensor for humidity measurement. The humidity sensor consists of 2 metal electrodes with a moisture-absorbing material, typically a salt or conductive polymer, placed between them. As the surrounding humidity increases, this material absorbs water vapor, causing the capacitance between the electrodes to change. By measuring this change in capacitance, the sensor is able to calculate the relative humidity of the air. For temperature measurement, the DHT sensors use an NTC thermistor. A thermistor is a component whose resistance changes significantly with temperature. The term NTC stands for negative temperature coefficient, which means that temperature and resistance have an inverse relationship. As the temperature increases, the resistance of the thermistor decreases. This behavior is clearly visible in a temperature versus resistance graph for an NTC thermistor. When the temperature rises, the resistance drops, and when the temperature falls, the resistance increases. On the backside of the sensor, both sensing elements are connected to a small integrated circuit, IC. This chip reads the raw temperature and humidity signals, applies factory calibration, converts the analog values into digital data, and outputs a clean digital signal that a microcontroller, such as an Arduino, can easily read and process. The DHT11 and DHT22 share the same 4-pin layout. The VCC pin supplies power. Although the sensors operate from 3.3 to 5 volts, using 5 volts is recommended. At 5 volts, the sensor can be placed up to 20 meters away, while at 3.3 volts, the cable length should be kept under 1 meter to avoid voltage drop issues. The data pin is a digital output that carries temperature and humidity data. Both sensors use a proprietary single-wire, half-duplex, timing-based protocol and an open drain configuration, similar to I2C. Because of this, a pull-up resistor is required between the data pin and VCC. The NC pin is not connected and can be ignored, and the GND pin is connected to ground. Wiring the sensor to an Arduino is very simple and identical for both models. We will connect the VCC pin to 5 volts, GND pin to Arduino's ground pin, and the data pin to digital pin 8 on the Arduino. Finally, we add a 10 kilo ohm pull-up resistor between the data and VCC lines, unless you're using a breakout board, in which case the resistor is usually already included. With the hardware connected, let's now understand how the DHT11 and DHT22 communicate. For this, let's look at the timing diagram of the data line. When the bus is idle, the data line is held high by the pull-up resistor. Communication begins when the Arduino sends a start signal by pulling the data line low. For the DHT11, this low pulse must be at least 18 milliseconds, while for the DHT22, a low pulse of at least 1 millisecond is sufficient. The Arduino then releases the line and pulls it high for 20 to 40 microseconds. Next, the sensor response phase begins. The sensor pulls the data line low for approximately 80 microseconds, followed by a high pulse of about 80 microseconds. This response confirms that the sensor is present and ready to transmit data. After the response, the sensor transmits a 40-bit data frame consisting of 5 bytes, 16 bits for humidity, 16 bits for temperature, and 8 bits for a checksum. Each bit starts with a 50 microsecond low pulse, which acts as a synchronization signal. The value of the bit is encoded in the duration of the subsequent high pulse. If the high pulse lasts for 26 to 28 microseconds, the bit is interpreted as a logic 0. If the high pulse lasts around 70 microseconds, the bit is interpreted as a logic 1. This sequence repeats for all 40 bits, which are transmitted in the following order: humidity high byte, humidity low byte, temperature high byte, temperature low byte, and checksum. Once transmission is complete, the sensor releases the data line, allowing it to return to the idle high state. As you can see, timing is critical when communicating with DHT sensors, which is why a dedicated library is typically used. 2 popular libraries are commonly available: the DHT library by Rob Tillaart and Adafruit's DHT library. Here, we have 2 sketches that essentially do the same thing: measure temperature and humidity and display the readings on the serial monitor. The sketch on the left uses the DHT library by Rob Tillaart, while the sketch on the right uses Adafruit's DHT library. Let's begin with the left sketch, which uses Rob Tillaart's DHT library. To install this library, we go to the Sketch tab, then click on Include Library, and then navigate to Manage Libraries. In the Library Manager search bar, we type DHT-lib and install the library created by Rob Tillaart. Now that we know that our library is successfully installed, let's look at the code. At the top, we have included the DHT library using the include statement, and then we have created a DHT object that will represent our sensor in the code. We create our object by first writing the name of the library, which is DHT, followed by the object name, which could be anything. We will call our object DHT as well, but written in capital letters. In the setup section, we start serial communication at a baud rate of 9600. This allows our Arduino to print the temperature and humidity information on the serial monitor. In the main loop, we will first read data from our sensor using either the read22 function for a DHT22 sensor or the read11 function for a DHT11 sensor. Keep in mind that you need to uncomment the line that matches your sensor type and comment out the other line. We will use the read11 function here as we have a DHT11 sensor connected to our Arduino. The read11 and read22 functions handle the complete DHT communication sequence. They initiate communication with the sensor, receive and decode the 40-bit data stream, verify the checksum, and, if the read is successful, store the resulting temperature and humidity values in the temperature and humidity member variables of the DHT class. Both functions take a single parameter, which is the Arduino digital pin connected to the sensor's data line, and they return an integer status code that indicates the result of the communication. If the function returns 0, the read operation is successful. In the library, this value is defined as DHT-lib-OK, so the numeric value 0 and DHT-lib-OK can be used interchangeably. If the function returns -1, which is defined as DHT-lib-error checksum, it means the checksum verification failed and the received data may be corrupted. If the function returns -2, defined as DHT-lib-error timeout, it indicates that the sensor did not respond within the expected time window. Now that the data has been successfully read and stored in the temperature and humidity member variables of the DHT class, we can access these values using the name of our object, DHT, followed by the dot operator and the corresponding member variable name. Both of these variables are of the float data type. We've already discussed classes, objects, and member variables in one of our previous videos. So if these concepts are still unclear, we highly recommend watching that video first. We begin by retrieving the temperature value using DHT.temperature and storing the returned floating point value in a variable named T. This returned temperature value is provided in degrees Celsius. Next, we retrieve the humidity value using DHT.humidity and store the returned floating point value in a variable named H. This value represents the relative humidity as a percentage. We then print these values to the serial monitor in a clean and readable format, displaying the temperature in both Celsius and Fahrenheit. Since the sensor reports temperature in Celsius by default, we convert it to Fahrenheit using the standard conversion formula shown. Finally, we introduce a 2-second delay before taking the next reading. This delay is essential because DHT sensors require sufficient time between measurements to operate correctly and provide reliable results. Now let's upload this code to our Arduino. After a successful upload, we'll open the serial monitor, where we can see the temperature and humidity readings updating continuously. The sensor initially shows the normal room temperature. If we gently blow air from our mouth onto the sensor, you'll notice that both the temperature and humidity values increase. This happens because our breath is warmer and more humid than the surrounding air. After a short time, once the airflow stops, the readings will gradually return to their original values. Now, before we look at the second sketch, which uses Adafruit's DHT library, let's replace the DHT11 sensor in our circuit with the DHT22 sensor. Since both sensors share the same pinout, we can simply swap the DHT11 with the DHT22. No additional wiring or circuit changes are required. This interchangeability is one of the biggest advantages of these sensors. Now let's move on to the code. As before, we'll start by installing the Adafruit's DHT library. We go to Sketch, Include Library, Manage Libraries to open the Library Manager. In the search box, we type Adafruit DHT. Locate the DHT library by Adafruit and click Install. After clicking Install, a pop-up will appear asking if we would like to install the Adafruit's Unified Sensor library as well, which is required by the DHT library. So we will click Install All to install the necessary dependency. Now let's get back to the code. At the top, we have included Adafruit's DHT library. Next, we define two constants. First is the DHT pin, which specifies the Arduino digital pin connected to the sensor's data line. Second is the DHT type, which indicates the type of DHT sensor being used. You can simply uncomment the appropriate line depending on whether you are using a DHT11 or DHT22 sensor. Next, we create an object of the DHT library or class, which will represent our sensor in the code. To do this, we write the class name DHT, followed by an object name, which can be anything. Here we will name our object DHT as well, but in lowercase. When using Adafruit's DHT library, we must provide two parameters while creating the object. The first parameter is the digital pin to which the DHT sensor is connected. So we have passed the constant DHT pin as the first parameter, which holds the value 8. The second parameter specifies the type of DHT sensor being used. So we have passed the constant DHT type as the second parameter, which holds the value DHT22. Inside the setup function, after initializing serial communication, we call our first Adafruit's DHT library function, named begin. This function initializes the sensor and configures the required timing, and it must be called inside the setup function. In the loop function, we start with a 2-second delay. This delay is necessary because the DHT sensors have a limited sampling rate. The maximum sampling rate is 2 seconds for the DHT22 and 1 second for the DHT11. Reading temperature and humidity using Adafruit's DHT library is very straightforward. Unlike the DHT library by Rob Tillaart, where a single read function stores values into variables, Adafruit's library provides separate functions for reading humidity and temperature. To read humidity, we use the read humidity function. This function returns the relative humidity as a float value in percentage. If the reading fails, it returns nan, not a number. In our case, we store the humidity value in a float variable named h. To read temperature, we use the read temperature function. This function takes one Boolean parameter. If set to false, it returns the temperature in Celsius, and if set to true, it returns the temperature in Fahrenheit. The return type is also float, and if the reading fails, the function also returns nan. In our code, we read the temperature in both Celsius and Fahrenheit and store the values in float variables t and f. Finally, we check whether any of the read operations failed. This is done using an if statement along with the isNan function. This function takes a single parameter, the variable to be checked, and returns true if the value is nan, otherwise false. In our case, we check the variables h, t, and f. Using the logical OR operator, if any one of these values is nan, The condition becomes true and the code executes a return statement, which exits the current loop iteration and starts over. Next, the Adafruit's DHT library also provides a function called compute heat index, which is used to calculate the heat index in both Fahrenheit and Celsius. The heat index is often referred to as the feels like temperature because it takes into account both the air temperature and the relative humidity to estimate how hot it actually feels to the human body. The compute heat index function takes 3 parameters. The first parameter is the temperature value as a float. The second is the humidity value, also as a float, and the third is a Boolean value. If the Boolean value is set to true, it indicates that the temperature value provided is in Fahrenheit. If it is set to false, it means the temperature value is in Celsius. The function returns a float value representing the heat index in the same unit as the temperature provided. Finally, we print all the readings to the serial monitor in a clear and organized format. Now let's upload this code to our Arduino. And after a successful upload, let's open the serial monitor. Initially, the sensor will display the normal room temperature and humidity. Again, we gently blow air from our mouth onto the sensor, and you'll notice that both the temperature and humidity values increase. After a short time, once the airflow stops, the readings will gradually return to their original values. And that brings us to the end of this video. We hope you found it helpful. Be sure to check out our channel and visit our website for more content like this, and we'll see you in the next one.